All right, this is our last day of our gerrymandering week. Right, so gerrymandering is the process of drawing new districting maps to favor one group or another, so maybe favor a certain political party over another. And this is a pervasive problem in the US, right? We have a system that is designed for certain reasons, but opens the door for partisan groups to literally rig the game in their favor. So we can discuss the merits of setting up our system the way it is. But currently, there's not much to stop the states from drawing these maps really however they want, apart from the occasional Supreme Court challenge, where we've seen the Supreme Court is fairly reluctant to throw out any state drawn map. The one I've been focusing on is this 2018 Pennsylvania case, where the Supreme Court decided that the map drawn was invalid, was partisan gerrymandering in favor of the Republican Party. And because of that, they got rid of the map, drew new ones, and we actually ended up seeing a fairly substantial shift in 2018 towards a more proportional balance in terms of representation from Pennsylvania. So today we're talking more about where the math comes in for how we can identify when gerrymandering has taken place. In the past, these arguments have often been about the size and shape of the districts, making arguments about the compactness, that a particularly strange looking district must be evidence of gerrymandering. But especially now that we have access to modern computers, the shape of a district really isn't necessarily a great indicator. It's possible to draw maps that are heavily rigged towards one party and still have the map look reasonable, look like we have reasonably compact and neat looking districts. We don't necessarily need those crazy spindles that we've seen in some past gerrymandering attempts. That said, alongside the developments of using computers to gerrymander, we've also had developments in using computers to identify gerrymandering. And this is an area of math research that is very new, that a lot of these tools were developed in the past several years. Much of what I'm talking about today is the result of research led by Professor Mundunchin at Tufts, who has been working on this and has testified in front of courts of saying, hey, these are examples of gerrymandering because of blank. And so today we are filling in that blank. We're saying, right, what arguments are we making? So if we're not focusing on the shape of the districts, maybe we can use something like the partisan bias or the mean median score, or one of these other metrics of how much a map favors one party over another. That said, just because a map has a partisan bias score or a median mean score, that doesn't automatically mean that there was intentional gerrymandering that happened. So let's look at an example that illustrates how even just the distribution of people within a state can put a party at a disadvantage. And that's not necessarily the result of some nefarious district drawer. It's just the way that people are distributed. Last time we worked with a new state, Squaretopia. Well, we've got an even newer state. Now we have North Squaretopia. North Squaretopia has a total of 9 counties, and due to its size, it's allocated 3 districts. So notice that most of the counties in North Squaretopia have the same type of distribution. 55 people in each county support Party A, and 45 people in each county support the blue party, Party B. However, there is one district that is very heavily Party B, which brings the total distribution so that across North Squaretopia, Party B is favored by a somewhat narrow margin. So if we're the map drawers and we get to choose what the districts look like, we could, for example, say, let's just take the vertical line districts. Maybe these are the way the districts should be drawn. Maybe horizontal, maybe something involving something that looks somewhat like this. There are several different ways of drawing these districts. However, for this particular example, it doesn't really matter how we draw them. Let's take the vertical case. So in the first 2 districts, well, each county has the same distribution, so across the board, in the first 2 districts, the orange party wins. In the 3rd district, the blue party wins. Right? If we looked at a different way of drawing these districts, there will always be 2 districts that look identical, and then the 3rd district, the one that includes this bottom right county, will always favor the blue party. So no matter how we draw the districts, 2 districts will be won by the orange party, and 1 district will be won by the blue party. So even though the blue party has more voters, more people in North Squaretopia want to vote for the blue party, no matter how the districts are drawn, In an election, the Orange Party will win 2 representatives and the Blue Party will only win 1. So this seems unfair. It certainly seems like the party that has a majority support should get a majority of the seats. But this isn't unfair because of gerrymandering. It wasn't the action of drawing the districts that led to this discrepancy. It was the distribution of the population that made it difficult for any map to support the blue party. So this is a well-documented trend, at least in the US. Districts that more heavily favor the Democratic Party tend to do so by margins greater than the districts that are very heavily favoring the Republican Party. The very heavily red areas of the country are typically something like 70 or 80 to 30 or 20, whereas the extremely blue districts are favoring the Democratic Party by as much as 95% to 5%. An important note is that I'm not talking about population density. Especially in recent years, Democrats have done better in cities with higher population density. This is certainly a trend, but that's not what I'm talking about here. Because each of these districts are drawn to have the same population, we can account for the fact that we've got denser populations. They'll just have smaller geographic regions. Right? So we're not talking about population density. We're talking about the difference or the margins that occur in Democratic strongholds versus Republican strongholds. Anyway, the point of all this is to illustrate the fact that just because a map, so let's take this one, gives us a situation that has a partisan bias score or some non-zero median mean score, that doesn't mean that it's the map drawer's fault. But the point of today is to talk about how we can identify situations where the map drawing process gave one party an advantage, not just the general geography. So in this particular example, we could calculate the partisan bias. We could calculate the median mean score by finding the seat vote curve. So here's the actual result that we saw. The blue party won slightly more than 50% of the vote, but still won less than 50% of the seats. We could continue out the rest of this seat vote curve and it would look something along the lines of something like this. Because we have a non-zero partisan bias score, and because we have a non-zero median mean score, this is an indication that the blue party is at a disadvantage. And that's sort of inarguable here. However, as we saw, this was independent of the way that the districts were drawn. So the problem wasn't with the map drawing, the problem was with the setup. That said, with regular Squaretopia, we saw that by drawing different maps, it certainly is possible to rig the game in favor of one party or the other. Okay, so how might we distinguish between these effects of an advantage because of the map being drawn and an advantage because of the geography or the distribution of people? Well, let's use, for example, our median mean score. So this red line is representing the median mean score for the Pennsylvania map before it was thrown out by the Supreme Court. So it had a partisan bias score of something over 0.06, which is a lot. So you could look at that and say, oh, well, maybe that was just because of the distribution of people. Well, to determine that, let's compare that median mean score to typical median mean scores. So if we can have a computer draw a bunch of random maps. So here, I believe the computer drew 1 billion maps and calculated the median mean score for each of these. So in a sense, we're taking a random sampling of the possible maps that are being drawn. And there's a lot more to it than that, and we'll talk about that in a moment, but this is the general idea. If we want to determine if a map is gerrymandered, we can compare that to what typical maps look like. And if it has a partisan bias that's significantly different than those, like this, then that's evidence that the map itself is giving an advantage, not just the geography. Notice that this shape is not centered at 0. 0 would be no partisan bias. So because of the geography, the distribution of people in Pennsylvania, there is an inherent partisan bias towards the Republican Party of about 0.01 partisan bias score. So in a sense, that's what we would expect a fair map to even include. So by default, we would expect maps to be at least slightly Republican favoring. However, this case is extremely different. When we were talking about normal distributions, we typically didn't even focus on situations where we were more than 3 standard deviations above or below the mean because that was just so unlikely. Those numbers got so small. Here we are quite a few standard deviations away from the mean. The likelihood that this extreme of a partisan bias can happen just due to random chance is so vanishingly small. So in that 2018 Supreme Court case that threw out the Pennsylvania map, there were many arguments as to why the map was gerrymandering, but this was actually one of the main reasons that the Supreme Court finally sided with the challengers and decided that, hey, this seems like evidence that this was in fact due to partisan gerrymandering. Okay, I glossed over a key piece here. How do we construct this set? How do we come up with the billion typical looking maps in the first place? This is actually a fairly tricky thing to do. There are a finite number of options. Remember, we typically work with precincts, so individual regions aren't split by the district maps, but the number of different maps that we can have is finite, but is incredibly big. So let's look at the state of Iowa. Iowa gets 4 districts because of the census information, and they happen to have a law that each county, so we have 99 counties, each county has to be completely contained in any single district. So we can't have the districting lines break up a county. So this is actually a pretty big restriction. Our building blocks of our districts are entire counties rather than precincts, which are like neighborhoods. So the number of possible options in Iowa is much smaller than the number of possible options in just about any other state. That said, there are an incredible number of different ways of splitting 99 counties up into 4 districts. There are restrictions, these things have to be connected. However, the number of possibilities for this is something akin to our number of possibilities of ordering a deck of cards. Earlier in the semester, I went on and on about how mind-blowingly large that number is. A similar situation is happening here in Iowa, and a much, much bigger situation is happening in other states like Pennsylvania, where we're not working with only 99 building blocks, we're working with thousands of building blocks for our districts. So it's not possible to check all of the possible districting maps. There are just way, 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 way too many of them. Instead, we want a collection that is a representative sample of what the general population of maps look like. How to construct that, though, is actually a little bit tricky. We could start off by drawing a few, and that would give us some, but how do we know that the collection that we draw isn't biased in some way? Maybe we're only drawing maps of a certain type, and maybe we should be considering some other type of map as well. So here's an answer to this. Rather than working with a state like Iowa with its 99 building blocks or Pennsylvania with its thousands of building blocks, let's work with North Squaretopia, which only has 9 building blocks. And this one is actually small enough that we can list out all of the possible ways of drawing a map. That's not something that we can do for the larger states, but hey, simple example. So one of the ways of drawing 3 districts out of these 9 counties would be the vertical way. So let's represent that with a graph. We can use this disconnected graph to represent our districting plan of having these vertical districts. We could represent the horizontal districts with another graph. So really any graph that follows these rules, that partitions this 3x3 grid up into 3 separate connected pieces, is equivalent to a valid districting. This one is the districting map that looks like this, which is a perfectly reasonable way of dividing this map up into 3 pieces. Okay, so we can imagine the entire collection of these, and I believe I'll have you do that in class, but in general, that collection is too big to work with. So how do we come up with a procedure of picking out a collection of them, a subset of them, that reflects the general behavior as a whole? So maybe just a good random selection. Well, one thing that we can do is we can imagine the graph of possible mappings, the graph of possible districting plans. So what I mean is we're taking a graph of graphs. Each of these, each node, each vertex of our graph of graphs is in itself a valid map. So this first one is a valid way of districting North Squaretopia, The second one is also a valid way of districting North Squaretopia. So we've got a whole bunch of vertices that correspond to all of the possible maps. Let's also say that two maps are similar, or that their vertices are adjacent, in other words, that there's an edge connecting them, if they are related in some way. And the way that we'll define related is this following swap move. So I would say that this map and this map are in fact related because we can get from one to the other by two districts deciding to trade a single county or a single precinct. So what's happening here is in this first map, the orange district is saying, hey, blue, do you want this county? And the blue district says, ooh, yeah, I want that county. I'll trade you this county for it. So this county gets swapped to orange, and this one gets swapped to blue. In other words, this county becomes a part of the blue district, and this lower county becomes a part of the orange district. And that's all we're doing. Two districts are trading a pair of precincts. Right. So because of that, these two are connected. There are other maps that are not connected to these. So we can imagine the big graph of all of the possible maps where there are edges connecting the maps that are somewhat similar, at least similar to this swapping a precinct rule. Okay, how does this help us? Well, remember, this graph or this collection of maps is incredibly large. And what we're after is a way of systematically picking out a few randomly selected maps. Right? So one way to do that is to pick a starting location and then go on a random walk throughout this graph. So let's start here and say, all right, let's randomly choose a direction to go. Remember, we did random walks on a line where I flipped a coin. Maybe here we've got 5 choices to choose from. We come up with some random number generator to say which way to go. So we randomly choose to go here, and then maybe back, and then up, and we go on a random walk throughout this graph. So while the size of this graph is huge, the diameter, or the longest possible distance between 2 points, is actually manageable. And as long as the length of our random walk exceeds the diameter by some amount, maybe let's say doubles the diameter, our endpoints are actually going to be fairly reasonably well distributed amongst this really, really big graph. So if we go back to the question we're actually after, which is how do we come up with the typical maps? What we can do is we can say, all right, if I want a billion maps in this collection, and if I've determined that this big graph, the total set of possible maps, has a diameter of something like 1,000,000 steps, which is a lot, but is not too much for a computer, we can start at a point and go on a random walk throughout the graph, maybe 10 million steps, see where we end up, calculate that vertex's map's partisan bias score, or median mean score, calculate that, and then do so for another, let's say, billion maps. So that's how this set was collected. It's a very large set where each element, each point, each data point in this was generated by going on a long random walk in the graph of possible maps. Okay, so that's pretty much all I have. So it's worth pointing out that this is not the only answer. There are many different competing answers for how we can address or how we can identify gerrymandering in various contexts. This is one of many, many tools. However, it does bring together a bunch of the ideas that we've talked about so far in discrete math. So I think it's incredibly cool that these techniques are being developed over the past few years, are being implemented in Supreme Court arguments, and actually ends up swaying the court, and you could argue changing history, which I think is really cool for some new math to be doing. Just a few days ago, the census report came out telling us which states are gaining or losing seats in the House of Representatives starting in 2022. So starting now, the various states are going to be redrawing their district maps. Over the next few months, not only will we be seeing new maps that are released by the states and saying, hey, this is our map, but we'll also likely be seeing challenges to these maps on the basis that, hey, they are partisan gerrymandering. So it seems incredibly likely that many of these states will be challenged with whatever map they come up with. So I'll certainly be watching to see what happens, and fingers crossed that if there are issues of gerrymandering, that the courts will take action, and maybe some of the newly developed math can help sway them in the right direction.